As a quick review from yesterday, we now have concavity as part of our analysis of a function. And if a function is concave up, that means that it's opening up. And it also means that the second derivative is greater than 0. But remember, that implies that the derivative is increasing. Now, if the derivative is increasing, that just means that these tangent lines are continuing to get bigger and bigger. Now, concave down means that the graph is opening down, which also means that the second derivative is negative. But with the slope idea, we would say that the slope, or the derivative, is decreasing, which means that these tangent lines just keep getting more and more negative. Well, when concavity changes, we have an inflection point. And an inflection point is always a place where we see the concavity changing from either concave up to concave down, or vice versa. But I want you to understand that the graph doesn't have to curve exactly as I drew it here. In fact, I can be concave up, but never turn, and then I can become concave down. So what you might see here is, in a sense, half of each of the concavities, but they're still changing at this inflection point. Let's analyze some, I'll call them some special functions. Let's analyze them for the works, and we'll start with y equals x squared minus 4x plus 5 from -2 to 3. Now, the good news about all of this is that we still start with the derivative. And the derivative, as we said in the last lesson, is still really where it's at, where most of our answer is found, where we get most of our analysis. So we'll do the derivative, we'll set it equal to 0, and we will solve for x. Now remember, when you solve this for x and get x equals 2, what you just found is a critical point of the first derivative. And that would imply that this has the potential to be an extrema. Now, the reason I say it has the potential to be an extrema is because we don't really know until we put it on our first derivative number line. But we put the number 2 on here, and we'll find a couple numbers on each side of 2. Maybe 0, since it's there, and maybe the number 4. But again, it really doesn't matter, as long as you're plugging them back into the derivative. Now, when you plug 0 into the derivative, you get 0 minus 4. That comes out to be negative. When you plug 4 back into the derivative, right here for x, you get 8 minus 4. And of course, that comes out to be positive. Now, at this very moment, I'm able to make the conclusion that 2 is a minimum. That's because, of course, my graph is going down, and then it appears that it's going to switch and start going up. And that was all based on the negative slope and then the positive slope. Let's find the second derivative. Now, the second derivative is kind of interesting because it comes out to just be 2. What does this mean for the concavity? And what does this mean for the inflection point? Well, let's still set it equal to 0, because that's always your next step. But when you set it equal to 0, you quickly come up with the conclusion that this is never going to happen, which means that there is no critical point. In other words, there's no inflection point. You see, there's no inflection point because there's no place where the second derivative is equal to 0. What does this mean for the number line? That is the second derivative number line. Well, it means two things. First of all, there's no point to put on it, but that doesn't mean that there's no value of the number line. In fact, the value of your number line is shown right here with the number 2. Since it's positive 2, that means that my entire second derivative is always going to be positive. Remember what positive means? It means concave up. Well, is that the kind of graph that we have? Is that the kind of graph that we are expecting? if you go back up here to the one that we sketched, you can see that that's exactly what we did. So you might say here that the second derivative only confirms what we anticipated, and that is that we have a parabola that is opening up. Now, let us not forget about these endpoints, and it's easy to do. In fact, it may have been smart to put these endpoints on our number line to begin with, but I can still put them there now so that I can keep in mind that these endpoints are going to be creating some type of maximum or minimum. In fact, we can already conclude that they're each going to be a type of maximum since they are in a relative position. Let's go to our final conclusions. And our final conclusions ends up being a rather large box, but you want to make it complete and basically lists these out. On a test or quiz, I'll have a space for you to do this, but for now, I ask you to, again, make the list. So we've got our max min, we've got our increasing, decreasing, we've got our inflection point, and we also have our concavity. Okay, so most of this has already been determined from our number line, but let us make it complete. Again, the endpoints are going to each be maximums, and that's simply because of the behavior of the slope after this first endpoint. The behavior of the slope is that it's going down, and the behavior of the slope before this maximum, that is that the slope is going up. So that's why I'm able to say that -2 and 3 are maximums. Our minimum we concluded from the critical point analysis, but we'll get that in our list. Our minimum is going to be at 2. The graph is increasing to the right of 2, but it stops at 3, so we'll mark that at 3 instead of the whole way to infinity. And then it's decreasing from -2 to 2. I haven't actually talked about this, but technically you're never going to have a closed bracket for an increasing, decreasing interval because, well, when you get to a point, when you actually arrive at a point, you're neither increasing nor decreasing. You're actually just on the point. So the answer is always not a closed or not an equal to part of your interval, not a bracket, but always a parenthesis. Inflection points, we decided that there is none because the graph is always concave up. And again, it's concave up on my interval. My interval that we started with was -2 to 3. Once again, I'm not going to include the endpoints there, and it's never decreasing. It's never concave down. Let's complete these y values. Remember that you simply plug each of the x values back into the original equation, and when you plug in -2, you get 17. When you plug in 3, you get 2. And when you plug in 2, you get 1. And these numbers also confirm the idea of being maximums and minimums. As you compare these y values with each other, you can make the same conclusions. Let's analyze another function for the works. Here we have y equals 5 minus x to the 1/3. Now remember, we're trying to analyze these using derivatives and second derivatives. In other words, we're not just typing this in our calculator. But don't forget that behind all of this, there is a graph that has some type of behavior. Well, the derivative is going to require us to bring down that exponent and subtract from the exponent. Of course, very carefully, when we subtract from the exponent, we get x to the -2/3. Now, it may be wise to, I would say, simplify this, especially if we're trying to think about how to do this without a calculator. Notice that I'm leaving 3 in the denominator. That's what it was to begin with. And I'm also going to flip and make a positive exponent +2/3. Well, we're supposed to set this equal to 0, but the only time that a fraction can equal 0 is if the numerator is equal to 0. That's never going to happen, so we don't get any critical point out of that. But we also want to set the equation equal to undefined, which basically means that the denominator is going to equal 0. And it looks like that happens when x equals 0. Now remember, what does this mean for x equals 0? It means that x equals 0 is a potential extrema. Of course, we don't know if it's an extrema or not until we put it on the derivative number line. All right, so we'll put x equals 0 on the derivative number line. That gives us two sides, numbers that we can plug in. Any negative number will do, and on the right side, any positive number. Now, where are we plugging them in? Well, we're plugging them into the derivative. So that means I'm plugging in to this denominator. Now, if you take negative number to the 2/3 power without your calculator, it's kind of like you're squaring it, and then you're rooting it. Well, if you square a negative number, it's going to become positive. And when I root it, it's still going to be positive. When it all shakes out, the numerator is -1 and the denominator is positive. So, are you tracking? That means that we have a negative slope. Now, if I plug 1 into this derivative, well, the same thing's going to happen. So, interesting. It appears that I have a negative slope and then some more negative slope. Does that mean that x equals 0 is a maximum or minimum? Well, it actually means that it's neither. All right, well, let's continue to discuss and investigate this function, which is time for the second derivative. If I were you, I would just go back to the original form of this derivative, that is without the fraction, and just bring down -2/3, and when it meets -1/3, of course, we're going to get a positive 2/9. I'm going to continue to subtract from my exponent and get -5/3. Here I am in kind of the same situation. It would make sense to simplify this second derivative. Basically, we're going to make the exponent positive 5/3. Now, you're supposed to set the second derivative equal to 0. The only time that can happen is if the numerator is equal to 0, but of course that produces nothing. How about when the denominator is equal to 0? Well, it kind of produces the same value. What does this mean? Well, it means that x equals 0 is a critical point of the second derivative. So what we're going to do is put x equals 0. Oh, and by the way, that means that x equals 0 is a potential inflection point. Okay, keep that in mind. It's a potential inflection point. I don't know until I put it on the second derivative number line what may become of it. Do you kind of feel like you're in the same place? Well, yes, but no. You see, now we're going to plug these numbers into the second derivative. So when I plug -1 into my, I would plug it here into this denominator. It's going to be -1 to the 5th power. Well, that's an odd power, so that's still negative. And when I root that, since I'm doing an odd root, it's still negative. What's happening here is that when I plug in -1, I get a negative second derivative. Now, when I plug in +1 into my second derivative, that's a little easier to do because 1 to any power is still 1. Looks like that since I have a 2/9, that's going to come out to be positive. Now remember, this red negative sign and this blue positive sign actually describe the concavity of this function, which means I now have the ability to conclude that x equals 0 is an inflection point. That's because the concavity changes. So what kind of function do we have here? Can you picture it? Can you picture a function that's concave down, and then it's concave up, but yet it's always going down? Or should I say it's always decreasing, since up here we have negative slope and more negative slope. What kind of function is concave down, concave up, but always decreasing? If we were in class, I would pause here and let you try to draw this. So There's no reason you can't pause the video and try to draw it. And how did you do? This is a tough one. Sometimes it's hard to get your pencil to even draw this concave down, then concave up. And look, you're always going down. It's always decreasing. What did we just graph here? We graphed y equals 5 minus x to the 1/3. This is an interesting and special function, but we were able to analyze it completely with derivatives. And by the way, x equals 0, it's an inflection point, but it's not a maximum or minimum. Let's make our little list of answers here just a little bit shorter. Max min, you can just say none. Decreasing, always. It's increasing, never. We'll just leave that out. Inflection point, again, that's at 0. Now, by the way, if I plug 0 back into the equation, the original equation, I'll get 5, so we can fill that in. And then, again, concave up. Well, it was concave up for the second half of the interval from 0 to infinity, and it's concave down for the first half, negative infinity to 0. So check this out. You can actually use the second derivative, which again means concavity, to test for extrema, which mean, of course, maximum minimum. Now, I like to think of this as calculus common sense. Once you think about it, you too will say, oh my gosh, of course. So what do we have? We have some notation. Now, you're going to have to start to interpret this notation. You're going to see it on a test, and you're going to have to say, this is what this means. So if f prime of c is equal to 0, what does that mean? Yes, it means the slope is equal to 0 at c. But what does that mean? Well, it means that the tangent line is horizontal, right? All right, so we've got a point C where we have a tangent line that's horizontal. Now, we've got this other statement here. It says f double prime at C is less than 0. Again, what does that mean? Well, when you see double prime, you would say concavity. And when you see less than 0, you would say concave down. Now, think about this with me. What kind of extrema are we going to have if a graph is concave down? Picture it. Picture it. Picture concave down. Draw it. Draw it. What type of extrema are we going to have? That's right. We're going to have a maximum. And so if you have a tangent line that has a slope of 0, and if your graph is concave down, it has to be a maximum. And so the second derivative, the concavity, actually can tell us about max and mins. Are you ready to try it one more time? If f prime of c is equal to 0, you know what that means, right? That means that the slope is 0. And if f double prime is greater than 0, you know what that means, right? That means concave up. Well, picture it. Picture it. What type of extrema will you have if you're concave up? That's right. You'll have to have a minimum. You'll have to have a minimum. And so the second derivative is actually able to tell us what's true about our extrema. It gets fun when you actually use this test in an actual equation. So let me show you how to use it. We're going to try it for this problem where we're given f of 2 is equal to negative 3, and also that y prime, that means I'm giving you the derivative is x minus 1 squared times x minus 2. Now, if I want to do this problem, kind of like the same way we've always done them, I would start with the derivative, but again, it's worth noting that that is what you're given. And we would set that derivative equal to 0 because, of course, well, extrema always occur when the derivative is equal to 0, or I should say that's when they can occur. Now we end up with two values here. We end up with x equals 1 and x equals 2. That's kind of nice. The equation was already set up for us to solve for those values. Now, instead of putting those values on a first derivative number line, since we're doing the second derivative test, all I'm going to do right now is just kind of hold tight with these and remember them as potential extrema. But what I want to do is go on to the second derivative. Now, the second derivative looks like it's going to require the product rule. It also looks like it's going to require a little chain rule here because I got an outside and inside function. So let's do the product rule. Let's do first, that would be x minus 1 squared, times the derivative of the second, that would just be 1, plus, remember it's plus the second times the derivative of the first. Now the derivative of the first is going to require chain rule, so bring that 2 down, leave the inside alone, finish the outside derivative, and multiply by the derivative of the inside. But we end up with a couple extra 1s here that don't make a huge difference. Now, as a math student, which means you're also an algebra student, you'd want to look at this expression and recognize that it can be simplified. It can be simplified by doing some foiling, some combining like terms, and I'm going to go ahead and say that you guys would be capable of getting this to become 3x squared minus 8x plus 5. But you have to understand that you would need to simplify this so that we could set it equal to 0. Okay, if we're going to be doing the second derivative, we need our equation to equal 0, and now it's on to solving it. Remember, you have the quadratic formula that could solve these for the critical points, or, which is sometimes the case, it's factorable. And do you remember how to factor when the leading coefficient is something like a 3? All you got to do is come up with the numbers that multiply to be -5, but when I plug them in carefully, I would FOIL them to check to be -8x. So we end up with these two binomials. All right, now remember what's going on here. We are solving for the critical points of the second derivative. Those are known as potential inflection points. And so that's what I want to do with these two numbers, kind of keep them in my back pocket as, again, potential inflections. Now, the second derivative test allows me to take all this information and analyze it with a second derivative number line. Got to get myself a little bit of space here. Let's put on our critical points in the right order here. I would need a 1 and a 5/3. So we got our critical points. Remember now, this is the second derivative number line, so we're going to plug some numbers back into our second derivative. You can pick a number from this interval less than 1. You can pick a number between 1 and 5/3, and you can pick a number greater than 5/3. You could plug it back in to the simplified version. You could plug it back into the factored version. Make sure that you're able to plug numbers back in and deduce that we would end up with a positive concavity in this section. We would end up with a negative concavity in this section, and we would end up with a positive concavity over here. Let me get my colors right. Now, I don't know if you're able to picture this graph right now, but I do know that we can take our potential extrema and we can insert them oh so carefully into this number line. And the whole point behind this is if I insert them very carefully, I will be able to determine, based on that previous slide, if they are maximums or minimums. Are you ready? We're going to insert the number 1. We're going to insert the number 1, and oh, it looks like it's already on the number line. Ready? Let's insert the number 2. It probably would be right around here. So we've got x equals 2. Now, the important thing to understand here is that since 2 is in a concave up section, we with 100% certainty can say that it is a minimum. It's a minimum, okay, because the second derivative test says so. But if you look at my x equals 1, you should conclude that it is neither in a positive or negative concavity. It is actually not an extrema. Instead, it's going to be overruled and become the inflection point. And by the way, so is 5/3 the inflection point, because both of them are places where the concavity changed. Now, what kind of graph is concave up but inflects at 1, and then it's concave down, but it inflects at 5/3, and then at x equals 2 there's a minimum and it continues to be concave up? What kind of graph is this going to be? Can you picture it? Okay, again, if we were in class right now, there would be a little pause time. You could try to draw the graph. It is quite a challenging graph though, but let me kind of help you get started. We're going to be concave up. Okay, this is happening until I get to x equals 1. When I get to x equals 1, there's an inflection point, so I'm concave down. Now, notice that x equals 1 is not a maximum or minimum, it's just an inflection point. And notice that 5/3 is also going to be an inflection point, so it's time to switch to concave up. And would you look at what's happening here? Look at what's happening. I'm able to say that x equals 2 indeed is a minimum. In fact, it's the only extrema of this problem. And all of that was based on a very careful analysis of the second derivative.